So what we have in activity 4.1 is we have now that their velocity is varying. And we're given a table that gives their velocity at certain times and also a graph of the person's velocity as a function of time. So what we're going to do is we're going to use this graph and the notion that area under the curve will give us the distance traveled in order to estimate how far this person has traveled. So for our first calculation, we're going to use delta t equals 0.5 or 1/2. So what we're going to do is we're going to break up our t-axis into 1/2 second intervals. So we need to now figure out how to estimate the area under the curve. And there's several different ways. Actually, there's more than several. There's quite a few different ways, but we're just going to look at one. So what we're going to do is use rectangles to estimate the area under the curve. So I'm going to draw a rectangle here. All of them will have the same width. That's our delta t equals 0.5. I'm going to draw another one up to the function and then across until I hit 1. Here's another rectangle here, and I come across and down, and I'm going to draw one more rectangle here. So what we can see is breaking up the interval from 0 to 2 with a delta t of 0.5 leaves us with 4 rectangles to estimate the area. So what I need to do is figure out the area of each of these rectangles. Now notice each of them has a width of 1/2. And so what I really need are the function values at these points. And notice that these are the left-hand corners of the rectangle. So this is known as a left-hand rule or a left-hand sum. I could have just as easily used the right hand and drawn the top of my rectangles that way. So I've got a delta t of 1/2. So that's the width of all 4 rectangles. So now, instead of just multiplying each of them by 1/2, I'm going to use parentheses so the 1/2 will get distributed. And so what I need is v of 0 plus, now here's v of 0.5 plus v of 1 plus v of 1.5. Notice I don't use 2 because that would put me all the way up here and that would make another rectangle. We only have 4, so there's our 4 heights. What this is going to do is this is going to give us an estimation of the distance traveled between 0 and 2. So I'm going to call this L for the left-hand rule or left-hand sum. And if you calculate this, it comes out to be 3.75. And the units on that 3.75 are whatever our distance is measured in, miles, feet. Notice we were in miles per hour, so this is 3.75 miles. I believe earlier I might have said seconds. Notice t is measured in hours. This is a half an hour, 1 hour, sorry. Now again, we could have used a right-hand rule, and just to show you what that would look like, I'm not going to do the calculations in this particular video, but the tops of our rectangles would have gone the other way. So they would have looked like this. And so that would have been what's called a right-hand rule. And that would have been 1/2. And now instead of starting at v of 0, we would have started at v of 0.5. v of 0.5 plus v of 1 plus v of 1.5 plus v of 2. And that would have given us another estimate that we could have used to the area. And then if we wanted to, we could average the left-hand and right-hand rule to get a little bit more accurate. So these are all ways that we can estimate. I just decided to do a left-hand rule for this particular video. Now, how can we get a better estimate than even just estimating between 0 and 2? We can use more rectangles. Notice we have the data to go with a delta t of 0.25. And what you can probably see is if we were to make our rectangles with this new one, and I'm going to do right hand again, but now we're going to use blue, I am going to get a little bit better estimate of my area because it can account for more of the curvature. So we can see it takes up a little bit more of the area using more rectangles. And the more rectangles we use, the more it improves our accuracy. Ideally, we would like to use infinitely many rectangles, and we'll see how that's going to work out a little bit later in this chapter.